Alright, so let's look at the differential equation dy over dx equals negative 2x plus y, all of that squared, minus 7. And in this problem, they give us an initial value of y. When I plug in 0 for x, I will get 0. So it's an initial value problem. Now looking at this, it may look a little tricky. You might not have ever seen one like this before, but we need to do a substitution at the beginning, and then it'll turn into a variable separable method, and it is very easy to solve after that. So I'm going to set u equal to the inside of what's squared. So u equals negative 2x plus y. Now I need to take my derivative with regards to x, so dy over dx equals, my derivative of negative 2x is negative 2 plus my derivative of y is dy over dx. Now I'm going to plug this back into my original equation. So for my dy over dx, I get du over dx plus 2 equal to u squared minus 7. So from here, I'm going to subtract that 2 to the other side, so I get du over dx equals u squared minus 9. And that also is u minus 3, u plus 3. So now that looks like a variable separable method. We know that we need our u's on the left and our x's on the right in order to do the integration of both sides. So I'm going to take du and divide by that u minus 3, u plus 3. And I'm going to multiply that dx to the other side. Now this is going to be partial fractions. So we have 1 over u minus 3, u plus 3, and I'm going to separate that out. So I set that equal to a over u plus 3 plus b over u minus 3. On that right side, I want to get a common denominator like what's on the left. So I'm going to multiply that a times the u minus 3, so I'll get au minus 3a plus bu plus 3b, all over u plus 3, u minus 3. From here, I know that my bottom on the left and my bottom on the right are equal, so I can say 1 is equal to au minus 3a plus bu plus 3b. So now let's look at our u terms, our terms with u in it. So on the left, I have 0 terms with u, so that's going to be 0 equals, and on the right, I have a plus b, which I can turn that into negative b equals a. Now let's look at the terms of our constants. I have a 1 on the left and negative 3a plus 3b on the right. From here, I'm going to plug in this negative b for my a because that's what I solved in the first system of equation. So I get 1 equals negative 3 times negative b plus 3b. When I simplify this, I get 1 equal to 6b, which is 1 over 6 equals b. And here, when I plug in 1/6 for b, I get negative 1/6 equals a. So now, I can plug that back into my a over u plus 3 plus b over u minus 3. So, I get negative 1 over 6, 1 over u plus 3, plus 1/6, which is my b, times 1 over u minus 3. Now this is all still in terms of du, and I still have dx on the right side. Now from here, I'm ready to integrate. When I take the integral of both sides, with that first term, I have negative 1/6 natural log of u plus 3 plus 1/6 the natural log of u minus 3. And on the right, my integral of dx is just x. And don't forget the plus c, and in this case, I'm going to call it c1. But c is an arbitrary constant. So now, if I use my exponent rules, I know that when I subtract two ln's, I divide them. So I'm going to be left with 1/6 natural log, and my u minus 3 is going to be on top, over, since I'm subtracting, and then that u plus 3, equals x plus c1. From here, I'm going to try and simplify it and solve for u. So I need to multiply 6 to both sides to get rid of the 1/6. So I'm going to have a natural log of u minus 3 over u plus 3 equal to 6x plus 6c1 when I multiply by that 6 over. From here, I'm going to get rid of that natural log. So I'm left with u minus 3 over u plus 3 on the left. And then on the right, I'm going to do e to the 6x plus 6c1. And that can reduce to e to the 6x. Now from here, I want to solve for u. So in order to do that first, I need to multiply times that u plus 3 on the bottom. So I have u minus 3 on the left equal to, when I distribute that u plus 3, I have u c e to the 6x plus 3c e to the 6x. Now I'm going to get my u's on my left, so I'm left with u minus u c e to the 6x. I'm going to add that 3 over, so 3 plus 3c e to the 6x. On that left side, I'm going to factor out the u, so I have u times 1 minus c e to the 6x equal to, and factor out that 3, I'm left with 1 plus c e to the 6x. From here, I can divide by that left parentheses, so u is equal to 3 times 1 plus c e to the 6x all over 1 minus c e to the 6x. Now you get to this step and you are still in terms of u. So we need to plug back in what I got at that, what I substituted u in for, which was the negative 2x. I need to plug that back in for u. So from here, when I plug back in u, I have negative 2x plus y equals, and then whatever I had on the right side, which is 3 times 1 plus c e to the 6x over 1 minus c e to the 6x. Now for here, I'm going to solve for y, so I'm going to add that 2x over. So y equals 2x plus 3 times 1 plus c e to the 6x over 1 minus c e to the 6x. Now, this would be done if we weren't given an initial value. So if we look back, our initial value was y. When I plug in 0 for x, I get 0. So we need to plug in 0 for both our x's and y's and solve for c. So I get 0 equals 2 times 0 plus 3 times 1 plus c e to the 6 times 0 over 1 minus c e to the 6 times 0. So I know that this first term is 0, and I know that when I eventually multiply my bottom over, it's going to be multiplied times 0, so it's just going to be 0. So these terms are both 0. So I'm left with 0 equals 3 plus 3c, and I don't have the e anymore because e to the 0 is 1. So when I subtract by 3, I get negative 3 equals 3c. Divide by 3, I get negative 1 equals c. Now I need to plug that back in to this equation, and I get y equals 2x plus 3 times 1 minus e to the 6x over 1 plus c e to the 6x. And that is how you solve this differential equation using the variable separable method after you substitute u in at the beginning.